Good morning. I welcome you all to the Department of Telecommunication TSDSI Micro Workshop Series. This is workshop number 5 on advancing 5G towards 6G. This workshop is going to be about enhancing security, efficiency, and performance in beyond 5G networks. I welcome all the offline and the online participants here today. This is the agenda for the workshop. We'll first have introduction from Dr. Samar, and then Dr. Guna would be concluding. I welcome Dr. Samar to take over the stage.
I hope I'm...
If I may, I can give a quick introduction about you. Dr. Samar Shailendra is a Senior Standards Architect at Intel and the Lead Standards Delegate at India and 3GPP SA6. He's also working as Visiting Professor here at IIIT Bangalore. Currently, he's the Co-Chair of TSDSI Roadmap Committee and Vice Chair of TSDSI Study Group Networks. Samar sir, welcome to this workshop.
Thank you. Thank you very much. Thank you everyone for making this happen and being present at this workshop. As you might have realized, the name is a little strange, the micro workshops. That's very intentional. The reason being that we did not intend to have long workshops, a day or 2 or 3, because we realized that the very focus of the people does not span more than 2 hours for a workshop. So that's the intent, that why we have this workshop as a micro workshops. We aimed at a series of it, and we'll run it for just 2 hours. We'll have very focused talks from very distinguished researchers and the technocrats globally. The entire purpose of this workshop is to gear up standardization in India. So what the research we are doing, the industry is doing, the academia is doing, the startups are doing, and all those different people who are working across India in the world of technology related to telecom and other areas which are related like verticals, etc., work with them, be a platform to give them an opportunity to present the work, connect together, and make India proud in terms of this standardization. Probably some of us know, who have been working very closely with government and all, that the Prime Minister of India has given a vision that by 2030, we should become the global leaders in 6G. We should have 20% global contributions happening from India to the global SDOs. We tried to work it out. We figured out that unless we really ramp up our contributions, our growth globally, we cannot even reach close to that. The rate at which we are growing today, we will probably reach 3 to 4% of the global forum if we just grow by this rate. So these micro workshops is an attempt to make it much faster, make it much more rapid, so that we can reach closer, we can reach 20%. And if we couldn't do fantastically well, then probably we'll exceed that. Who knows? But with that, I welcome all of you to this micro workshop series. We'll be having a lot of technical talk. So I'm not going to do a technical talk today myself. I'll probably give you a bit of insights into the micro workshops. Then I want to orient you towards the position of TSDSI globally and a bit of introduction about 3GPP, because I believe a lot of us today do not even understand what India is, what TSDSI is, how we can really contribute to the global forum, and how we can create an impact. What we all see is companies like Qualcomm, Intel, Ericsson, and so on and so forth. Yes, we all aspire to be like them. We all aspire that our companies in India should become like them, but we don't know what we need to do to achieve that. So this is an effort in that direction as well. Thank you once again, Priya, to introduce me. So as you all know that I'm working very closely with TSDSI, and today I'll be talking about the entire 3GPP ecosystem and how TSDSI is placed with that. Some of you who know about the 3GPP is a partnership program, which is a consortium of different SDOs across the globe. So there are 7 SDOs as of today, and TSDSI is one of them. So we are the organizational partner, with likes of HC, ATIS, CCSA, TTC, etc., which are ranging from China, Europe, Japan, Korea, and United States. That essentially means we have equal amount of say in any standards which happen globally from India. How do we make that happen? That TSDSI provides a platform to all of us to become the individual member to 3GPP. So any company like Triple IT Bangalore is already a member of TSDSI. They can become the individual member at 3GPP and take their work, whatever research you are doing, to these standards. And that's the place when you actually monetize your research. I mean, I have been in academics for quite some time. I mean, I have been associated with Triple IT Bangalore. I have been working earlier at different places. And I realized that we researchers are very good in publishing. We publish papers. We don't know how to convert that into the real money. And standards is one of the ways to do it. Not an easy job to do. It's not that it comes very easy or handy or straightforward, but that's the way to do it. Money doesn't come easy. The other way which 3GPP ecosystem is consisting of is the market representative partners, or the MRPs, which are like the bodies across the globe, which are the consortiums or representative of industry in different countries, like COI in India. So all this together, the OPs, the IMs, and the MRP makes the 3GPP as an ecosystem. The OPs which I was talking of, Arab, ATIS, CCSA, HC, TSDSI, TTA, and TTC from Japan. So Japan has 2 OPs in the ecosystem. Yeah, that's just a quick glance at what the 3GPP is and how influential it has been over the past. So it is there for 23 plus years. So starting from the world of 3G when it called 3GPP, and before that it was a part of HC. So HC started working on the 2G standards. Then we realized the felt that you need a bigger partnership program independent of HC, and that's how 3GPP was born. And post that, we had the 4G standards, the 5G standards, and now we are in the world of 6G, and so on and so forth. So you see, that makes it a very important system. From a contributions or the impact point of view, you have more than 10,000 technical specifications which has been released, and the people who are there, like Professor Prem and others who work with the 3GPP, know that every specification is a lifetime work of a lot of people. We have over 100,000 contributions being provided by the members. It's a lot of technical groups, 16 technical groups. The number of companies are 750 plus. This is slightly old data. I've heard that it has already crossed 800. And 2,000 plus man years in cumulative meeting time. So what does IAMS are? So these are the IAMS is the place or the membership through which you contribute to the 3GPP. So TSDSI is a platform which gives you an opportunity to become an IAM. Through this IAM membership, you take the 3GPP membership and you go there and contribute to the larger ecosystem. A quick organization about 3GPP. So the topmost is the PCG, which is Project Coordination Group, which is like the governing council for 3GPP. Then it is divided into 3 verticals: the RAN group, the CT group, and the SA group. If you look at today's talk, it's primarily be focused more contributing to the RAN, which is the radio access network, which in itself is consisting of multiple working groups, which are focused on different aspects of the radio access network, like file layer, the resource layer or the MAC layer and things like that, the UTRAN, ONM requirements, protocols, conformance testing, and the RAN of the GSM or edge side. Similarly, the CT group is again consisting of multiple work groups which are focused on different aspects of the protocoling aspect when you build your network. And the SA group, which is the services and systems group, which is basically focused on the core network if you look at from the mobile network point of view. This is further divided into 6 working groups. The services, which is the one which basically lays up the requirement for your entire 3GPP. The architecture, security, codec and media management, and the applications. So if you look at from the work point of view, that how typically the work happens, excuse me, work happens in 3GPP. You start with the requirements, which is done by the SA1 group. followed by the architecture group, where SA6, SA3, and SA2 are the groups which work on the overall architecture of the network. Finally, it goes to the protocols aspect, which are the core terminal group, which builds your entire protocol specifications. The RAN group is little strange. They span across the architecture as well as the protocol groups, because a lot of work they do which belongs to the radio access network architecture. A lot of work they do which belongs to the protocol part of it. And followed by the stage 4, where you do all the testing and the conformance and things like that. This slide is very important to understand, where I'll probably spend 30 seconds, because if you want to play inside 3GPP, you should start from here. What we have been doing, we are trying to either come here, we say, okay, my research is being done, I'll try to put my work here, or I try to put my work here. Okay, I have developed a protocol, I will go and contribute here. Or if I am a radio access guy, I will go, okay, I'll go directly to the RAN group and try to contribute here. Nothing will work unless you enter into the system here. You cannot enter in between. You can exit, but you cannot enter. So be very mindful of the fact that if you really want to play, you have to be here. If you are not here, you are already lost. And from a release 19 point of view, if you look at what we are doing, the 5G Advanced, this group is concluding. This group will finish off in June, right? We are talking about 6G specification in 3GPP already, which is release 20. The discussion will start from June-July timeframe. So you have actually already lost 5G Advanced, in my opinion. You are already on to 6G, and this is the time to get in. So if you are looking at it, you have to be in 6G, otherwise you are gone. Okay, this is a small effort from TSDSI, what we have been doing. Oh my God. Sorry, I mean, somebody's, and this is called the Murphy's Law. When you don't want it, you will get it. So this is how the TSDSI has organized this entire effort on, how do we contribute from TSDSI to the 3GPP ecosystem. We have been planning this micro workshop 1, 2, 3. We had a lot of other workshops which has been happening. The release 19 work has already been started, which is ongoing. We are pretty much reached here. We have this workshop being planned in June, where this release 19 discussions will be happening. Then we have this packaging, which will happen in September. This is the SA packaging, and then you have the RAN packaging. And then from the December 23, your 6G discussions will start. So you're not far. 6G discussions are going to start in 23. So if you want to contribute there, you have to plan now. This is the time. So that's why this slide is very important, that you have to be very mindful of the time. Otherwise, I mean, like you prepare for your conference submissions, right? You plan at least 1 year in ahead if you want to submit in ICC, or if you want to submit in Globecom. You don't plan it 1 month before, at least 1 year. And if you look at this is even more critical from that. You have to plan at least 2 years ahead. Then you can make any impact. Okay, so this is some quick next steps. Of course, the micro workshops is one of the vehicle to get involved with TSDSI and 3GPP. You can contribute to release 19. Actually, I should change it. Now I should say contribute to release 20. 19 is almost over. But still, small window is there for 3 months if you can really launch over the existing work which has been agreed. You can reach out to us if you want more details. You can write to microworkshop@tsdsi.in for any detail, how to get involved, how do we work with them. You can join TSDSI to acquire the 3GPP membership. Please familiarize yourself with the working procedure. All of us are here. Pamela is here. She is a veteran. She has driven the entire 5GI from India, which all of us should be very proud of. Then these are some, mailing list and things like that. Some appeal from all of you. There are poll questions towards the end, especially for the online participants, because the people present here, we can talk to. The online participant, we don't get to talk to them. So please participate in the polls. That will happen towards the end of this workshops. You can also fill out the expression of interest. That will also be sent out by the IT team. Okay, and if you have further any details, please write to us. Yep, that's some important links. that's all from me today. Sorry for being a little overboard.
Thank you, sir. Thank you, Dr. Samar. Next on our speaking list, we have Dr. Das. He's our director and he's also a PI and a nodal officer of projects under the National Mission for Interdisciplinary Cyber Physical Systems in the areas of advanced communication systems from DST Government of India. His main research interests are IoT and wireless access networks, MAC, QoS, and power saving devices. He's also a technical steering Empower Committee member of multiple departments of Government of India and the Government of Karnataka, India. He's a fellow of IETE and IE. I extend a hearty welcome to Das, sir.
This slide is working?
Yes.
Okay. So thank you. And it is a really honor to welcome all of you to the IIIT Bangalore campus. Thanks to Pamela Madam, our who has been in the Director General of the TSDSI for a long time, and he practically steered India to one of the most prestigious standard called 5GI. Thank you for joining us, 5GI. So India, first time after independence, this has been TGPP. And yeah, so I can be in this zone. Okay, the camera is here. And thanks to Satyapriya Madam, she has traveled as a DDG, Department of Telecom from Chennai. She has traveled, and this shows that DoT is extremely serious for these kind of standards to push from India to the world forum, and why standard is so important for younger generation. I will quickly come to that. And secondly, Mr. Guna for thanking Dr. our Samar and all the team from the TSDSI and my professor colleagues, and also the researcher from the labs and also the students. So quickly, before I go into my talk, quickly why we have been talking about standard, particularly for the younger generation who have been attending. If you want to survive, or I'm using the very strong word survive in this world of communication, standard is extremely important, because first is product, which you are ultimately sold, where the companies make profit and give us jobs and research funding. But before going to the product, standard is extremely required, because without the standard, no product has been made in communication, first of all. Second, before product, then you have to have the IPR, and before that, you have to have the research and innovations. So whatever you do in the lab, now you should have to think on that. Why standard is important? Very simple example, look at these plugs. India, anywhere you go and put the plugs without thinking. And if these plugs without not being standardized, the distance between these two pins, the height, distance, the angle, and all, if not according to the standard of this one, your plugs system will not work in anywhere. So the standards leads to those kind of accuracy for the communication, the bit rate or the modulation techniques and protocols and all. So let me quickly, I thanks TSDSI for hosting this one here, and let me take a little pride from IIIT Bangalore. When TSDS was inaugurated in Delhi, I attended that, but after that, the first technical workshop, well, they asked me, I welcomed them. The first one was hosted in IIIT Bangalore for TSDS, the first technical workshop, and now the TSDS have grown very large and huge impact in the worldwide. It is very heartening to see that. Thank you all for hosting it again back in IIIT Bangalore. So as you know from the topic is that from 5G to 6G, mainly there are two things we are talking about. One is efficiency, another is security efficiency. Efficiency means the performance, and we all know what it means, the performance. If you look at, there are 5 to 6 major parameters like delay, throughput, packet drop, and all these error corrections, error bit rate or packet rate. These are the 5 to 6 parameters, along with security adding to that. Those are extremely important when you move from 2G to 2.5G to 3G to 4G, 4.5G, 5G, and now 6G and 7, and all those 7G and all which will come. So if you look at all those things are there, only a couple of things I will talk about which we missed in our discussion, which is already there. One is called green communications, which is important. Efficiency means all those points I say, is the spectral efficiency and throughput, delays and all. But energy efficiency, which has been very strongly and very deeply discussions happen from 4G onwards, because every bit we transmit, we consume energy. And if you look at telecom, is the second largest power consumption department or organization in the world, that after the railways. in the world. So this is the second. People don't know so much of carbon monoxide we are emitting to the world because of internet communication and telecommunication. So energy efficiency is one of the very, very important, because everybody has bits now and everybody is transmitting and receiving bits and we consume energy. Key technologies like massive MIMO, NOMAS, Milter, these are things are coming up, and people are working on the physical layer and all in this communication. Security in each layer. Security is everywhere, for starting from PHY to the applications layer. People are working, and these are going to be more and more complex as times to come. And also people talked about that quantum communication. I'm just adding it here because we are from the communication world, but quantum communication may take another 10 to 20 years from now. So to be reality, because they're in the labs and experimental level to the standards, then the product. So next to it, in these electronics communications, we have to be careful on this, on the security aspects. And network softwareization. Everybody talks about the softwares now because software defined network function virtualizations and all. But keep it in mind, the software and the hardware are in two different domains. Software is much slower in comparison to the hardware, but to looking at the flexibility and the compatibility and all, people have given stress to the software. So but software architecture, the execution speed has to be much faster and very close to the hardware speed, then software can be more leveraged. Why I'm saying this? Because in 5G we are talking about delays of an ultra reliable low latency 5 millisecond or 1 millisecond, like driverless cars and robotic operations. But when you go to 6G, because it's a path to 6G, then people will talk about 125 microseconds. So this is a nightmare for the engineers and the scientists of the communication world, that along with the system, because system consists of your hardware and software stacks. So what should be your architecture that you can lead to that kind of microseconds of delays, which will take you there. So now come all these things, virtualization and network slicing. I'll be talking about with Professor Joshna about that, or how it going to work to realize the 5G and 6G. Lastly, there are two bullets I'll be talking about. Potential beyond the 5G physical technologies like intelligent reflecting surface. Means this is not be in your transmitter receiver, but these walls will be full of your reflective surfaces, which will reflect your signals to the source receiver in a better efficiencies. And orchestration of this is a thing which we have not talked about. You see, nowadays applications are orchestration of multiple services. I call him and Mr. Guna, hey, how are you? He said, I'm in Bangalore. The moment, without telling him, I touched the Google map. I found out his location. So this is orchestration. From the voice, I added a Google map. Then I found out the nearest hotel to him where he is. Then I invite him for lunch today morning, today after lunch on the upstairs. So, so high-speed UAVs communication. So the multiple unmanned air vehicles are there. These are on the 6G areas problems. And at the end, everybody will survive due to the billing. But no one of us talk about the billing standardization is done, because the moment you increase the bit rate from gigabits like that 10 to the power 9, you're is 1 nanosecond bits. So how will count the bits to give you the bill, particularly the prepaid one? Postpaid one, okay, it is little easier, but not so easy. So this standardization in the billing is needed. It's a very complex problem. It cannot. So these are the things we have to think of because of the new 5G to 6G going on with respect to the speed. So I will take a couple of minutes more. These are my esteemed colleagues who works with us in these labs. Professor Josna, who works in network slicing, scheduling, 5G, privacy, security, and IoTs. I also work on Mac, particularly in quality of service and green communications, and also network slicing. Professor Priyanka works on cognitive radio, MIMO, and Amrita, Professor Amrita, machine learning and 5G beyond, millimeter wave communications, all are here. Vinod Reddy, Dr. Vinod is sensing, modulation and signal processing area he works, and Dr. Prem works on transceiver design and machine learning application, 5G and beyond, and hardware and design and all for the 5G, which is going for open radio access network. We as a group, 6 of us, along with our around 20 people working in our labs, you can visit our labs after lunch and see those works happening. And this is a thing which I wanted to talk about. IIIT Bangalore has made a Section 8 company called Comet Foundation. Comet stands for COM for communication, E stands for enterprise technology. So we are taking our research to the IPR, to the standardization, to the product level. So this Comet Foundation Section 8 company, which is being built by the Department of Science and Technology in IIITB as a technology innovation hub in advanced communication. So we are working on the enterprise level of technology. So So now I am coming to the Comet Foundation's contribution to this TSDSI and 5G and 6G. So if you look at our standardization efforts, is the IIITB Comet Foundation Research Group have been working for 5G and 6G standards. Dr. Arjat Kirni, who is in the part of our IIITB Comet Foundation collaborator, recently appointed as chair of Working Group 3 of SGSS group of TSDSI, and also Professor Kiran Kuchi and some of my colleagues together, he has written the 6G visions, and IIITB faculty members are working on with the group of the students and also the researchers and also the other institution collaboration on 6G standards. So they will be presenting their works, and you can look at that, all what is going on there. And also the co-chairs of standard and driven research implementation and oversight committee and standardization activity proposal accept at TSDSI, and first version of technical specification expected in the June. So we are also submitting from this group from IIITB Comet Foundation, all these things. And mainly we are working on two major problems. One is ORAN, Open Radio Access Networks, mainly on 5G advanced, and RIS, Reconfigurable Intelligent Surface. So this is the ongoing key projects and networking and communication. So because my time is almost run out actually. So this 5G advanced ORAN design and development and new prototype RIS added communications, smart radio environment, implementation, deployment of targeted user cases, hardware realization of 5G millimeter base stations, and we are doing the indigenous completely hardware board in IIIT Bangalore along with other areas, and non-contact cross-medium communications, ethical 6G. That is another interesting area. We are working with an international funding on this, and India and Australia is collaborating on that. Design analysis and real-time implementation of low complexity receiver and spectral efficiency channel estimation and all, and vital signs of in monitoring using FMCW radar. And another thing which we are doing very much, which we have not mentioned at here, I forgot for that, sorry. We are one of the leading researchers in spectrum auction, spectrum requirements. And true, Professor Sridhar is here. His book and his papers has been referred across the globe on spectrum selection. And in India last time, he also presented in highest level on his spectrum papers, how to auction the spectrums and where we should stop, how to pricing the spectrums and all. So he will be talking on that. So now I'm coming to the last slide. So this is my last slide on thanking you all. So if you have any questions, I'm always available and we can talk about that.
Thank you, sir. So we also have a lot of questions flowing in from our online participants. However, these questions will be answered at the end of the session if we still have time, or they will be answered via email if there's no time. Next on our list, we have Dr. Prem Singh. He's currently working as an assistant professor at IIIT Bangalore here. He has won numerous awards and accolades for his research in 5G wireless systems. Two of his recent papers have in fact been selected by IEEE Communication Society for the best OTFS and delay Doppler signal processing readings. His research interests include transceiver design for 5G and beyond wireless system. Dr. Prem, I welcome you to the forum.
Thank you. Okay, so the title of my talk is Low Complexity MIMO Receiver for High Mobility Applications. So to start with, there are some emerging high-speed vehicular scenarios. We have vehicular-to-vehicular communication, high-speed railway communication, communication in hilly regions, and drone communication. So the common thing here in all the emerging application is that there is a relative movement between the base station and users. And because of this relative movement, this is what makes a high-speed vehicular scenario challenging. Now, if you see the challenges, especially for high mobility applications with respect to receiver design. So we know that for a quasi-static channel, meaning that your channel remains same for a frame boundary, or you can say TTI, let's say 0.5 millisecond in case of NR. So in that case, that OFDM, which is the popular waveform for right from third generation cellular network to 4G and 5G, we can simply use one tap receiver, or you can say equalization, and that requires almost no complexity. So this is simply a division with channel coefficient and you are done. But when it comes to rapidly time varying channel, that happens because of the high degree of mobility between transmitter and receiver, and this makes your channel doubly selective. To put it in simple word, means your channel is not flat across the subcarriers of OFDM, and it is also varying with time. So that this channel is not flat across subcarriers means by adding cyclic prefix you can take care of that. But because of time varying channel, this OFDM results in intercarrier interference, which simply your one tap receiver or equalizer cannot cancel. So it demands a multi-tap equalization in high mobility application, and that has very high complexity. So the challenge is how to reduce that complexity. So in this talk, we look the channel not in typical time frequency domain. We say that, okay, you look the channel in some other domain called delay Doppler domain. And even if it's a highly time varying scenario, you will find a very nice multi-banded structure. I'll talk about that in subsequent slide. And you can exploit that to design a low complex receiver even in high mobility applications. And the algorithm which we are proposing is that it can be used for any multi-carrier waveform. It's not only for OFDM, the other multi-carrier waveform which are picking up, it can also be used for them. Okay, some of the activities with respect to this mobility applications start from release 16 of 3GPP. So there, this 5G standard, it expanded the 5G standard NR something called into NR side link, which particularly focusing on V2X. One of the focus is V2X, which comes under the umbrella of mobility applications. In release 70, there was a focus on communication in high speed train, which is again coming under high mobility applications. And release 18, we see it's targeting many things related to mobility, like improving latency, signaling overhead, interruption time. And one of the component, there are many component under this. One of the component is L1 and L2 based intercell mobility. In particular, you can say L1 based intercell beam management when there is a relative movement between base station and user. So in short, we can say that the features in 5G advanced such as MIMO or massive MIMO coverage and mobility evolutions will lead to improve end-to-end performance in 5G and beyond systems. So little bit of mathematics with respect to receiver design. So let us consider we have n symbols, or m subcarriers, since we are talking about multi-carrier waveform with the NT transmit antennas and NR receive antennas. Then the received signal is given by the vector R, where n is the noise with each element IID with variance sigma n square. And the transmitted symbol is S is also given here. Now, one important point here, if you see this matrix A, it differs for different multi-carrier waveform. So I'm taking the example of two waveform here, OFDM, which is the popular waveform, and it is also being used in 5G. And I'm taking one more waveform, orthogonal time frequency space, which is also picking up now. So the matrix A is given for these two waveform here, and this channel H. So this channel, the part of this is not the channel in time frequency domain or time frequency domain. This channel is in delay Doppler domain. Delay Doppler domain, which is a block diagonal matrix given here. Okay, so then this qth matrix of the block diagonal matrix H is given by this relation, where if you see HP is your channel gain between the UH transmit and VH receive antenna. Matrix pi, characterize the delay. Matrix delta characterize the Doppler. and KP and LP, they are the location of the pth path in the delay Doppler domain. Now coming to this, using the received vector R, if you see the linear receiver, or you can say one of the popular receiver called MMSC receiver, this is how you can calculate or you can estimate the data at the receiver. Now, so this is our MMSC receiver. So in this, if you see that matrix B, this is a unitary matrix which can be implemented using FFT, so does not require much complex operations. But precisely if you see this matrix inside the green box, it requires an inversion, and this inversion of a huge matrix. And so the precise problem statement is how to find low complexity solution for this operation. So this talk is going to address this. So as I said, the most expensive operation is the inversion of this positive definite matrix psi, and it requires order of m cube, n cube, or nt cube operations, and in practice these numbers can go high. For example, m, which is the number of subcarriers, if you see 5G NR, that the number of subcarriers are 4096. Similarly, you can have, let's say, depending on how many symbols you are transmitting in TTI, which depend on what numerology you are using in 5G NR, this number can also go high. So this is having very high complexity. So we address this problem, and the high level idea or the proposed idea is to exploit the structure of this matrix psi. It has a very nice structure in delay Doppler domain which can be exploited, and to reduce its complexity. And the proposed receiver results in a complexity of the order of mn nt log n, which is drastically lower than the conventional receiver, which has a very high complexity of the order of m cube, n cube, nt cube. So to design our low complexity receiver, we write this matrix psi in mn cross mn block matrices. So if you see any of its block, I have given the structure of this matrix, where these black dot shows that the non-zero elements. This is having a banded structure. This is in the delay Doppler domain. It is having a banded structure, and because of this, if you see this matrix psi, this is having a multi bands. So first of all, it's a sparse matrix. Sparse means there are very few elements are non-zero. Second, it's multi-banded, but its bandwidth is high. And when I say bandwidth, this is the definition of the bandwidth of a matrix. So let's say if you have a n cross n matrix, you define two constant k1 and k2, that is, let's say, lower and upper band. And if all the elements are zero outside a diagonally bordered band of this matrix A, then you can say that the bandwidth of this matrix A is maximum of k1 or k2, whichever is maximum, that is the bandwidth of this matrix. So what we do, we propose to reorder this matrix. So psi is having multi-banded and its bandwidth is close to full bandwidth. So we propose to reorder this bandwidth, and which consequently reduces its inversion complexity. And for that, we define a structure matrix of this psi. So at high level, when I say structure matrix, it's simply all the non-zero elements in matrix psi, you just represent them by 1 and rest of them are 0. And if you see that mathematically, this is how you can calculate the structure of this matrix. So this structure matrix psi s is indicating the sparsity pattern of matrix psi. And in this relation, if you see this is the Kronecker product, that circle and cross, this is the Kronecker product of two matrices. And the calculation of this matrix psi is depending on one parameter called alpha. And what is alpha? Alpha is simply the unit, the delay corresponding to the maximum channel delay spread. And for all these standard channels, this is typically known at the receiver. So maximum channel delay spread is typically known at the receiver. So I can say that the alpha is also known at the receiver in advance, because alpha is depending on tau max, which is the maximum delay spread. Second, M, number of subcarrier, which is also known at the receiver, and delta F is the subcarrier spacing of a multi-carrier waveform you are using. So all these parameters are known. So alpha can be computed at the receiver offline. So that is one of the important property of this proposed receiver. So alpha can be computed offline. This alpha is available, and because of that, this psi s can be computed offline. So the computation of psi s does not require any complexity. So it is already available at the receiver. Once you have psi, then you calculate something called permutation matrix P using this matrix psi. And for calculating permutation matrix P, we use something called reverse Cuthill-Mackey algorithm, quite popular algorithm. You can go to MATLAB, and there is a inbuilt function in MATLAB. You can directly use that. So now you have the permutation matrix P. So P is also available offline at the receiver, because psi s is known to the receiver. So P is also known to the receiver. So once P is there, now we reorder this matrix psi using this permutation matrix P. So if you see the figure, the top figure is showing the structure of psi. Then you operate with matrix P, and now you have a nice banded matrix whose bandwidth is very small in comparison to the original matrix. Now this matrix can be inverted with much lower complexity in comparison to that of the matrix psi. And to do that, so this is the slide which gives all the steps of the low complexity receiver. So you input the received vector R and the CSI, channel state information H. In practice, it is the estimated information, then the SNR, and it will give you the output of the output that is estimated data vector D. First is you compute the matrix psi, and there is the vector R bar shown on the slide. And then after that, the permutation matrix P, which is already available at the receiver, you operate with that and convert that psi into a banded matrix. And this psi, since it is this permutation matrix P, it does not change the semi-positiveness of the matrix psi. So this G can have nice LU decomposition, which we also call it Cholesky decomposition. And if you see the structure of U, this is the upper triangular matrix. It's shown in the figure. So this is also a banded matrix. Now you can simply invert G. So inversion of G is U inverse and L inverse, where both U and L are upper triangular and lower triangular matrix. Okay, now if you compute the this inversion using forward and backward substitution by exploiting this sparsity, the complexity is much less. And then after that, since you have reorder the matrix psi, at the end we need to reverse that reordering. So you operate with the permutation matrix P transpose, which will reverse the reordering, and this is how you can get the estimate of the vector D. So very simple and very less complex algorithm especially for high mobility applications. So some of the performance that how it is performing. So these two plots are showing the bit error rate performance of the proposed receiver. So I have taken two waveform. One is OFDM and second is OTFS, just for the comparison, to show that it is working for both the waveform. So the first thing, and for the simulation, we have taken a relative speed between base station and the user, that is the 500 km/h. We assume that extended vacuolar channel for the implementation. So the first thing, if you can notice, for both the OFDM and OTFS, the proposed receiver is having exactly same bit error rate as that of the conventional receiver. Means it is not making any compromise in the performance, meaning that it is not making any approximation. It is just exploiting the delay Doppler structure of the channel, reordering it, and then, so that's why both the receivers is having exactly same performance. And one more thing is that OTFS is performing better than OFDM. That is well known in the sense that since this is a high mobility application where there is a lot of intercarrier interference because of the time selectiveness of the channel, which this OFDM cannot cancel, and its performance are inferior. Whereas OTFS, it is doing all that processing in the delayed Doppler domain, so it is having better performance. Now coming to the performance of the complexity performance. So if you see here, I have compared with the conventional receiver and the proposed receiver, and I have also used two more receiver. That is MP is message passing, which is the popular receiver for waveform like OTFS, and there is one more receiver, maximum ratio combining. If you see the performance, the complexity is varying with the number of subcarriers. Still, the proposed receiver is having the lowest complexity. And if you see a scenario like massive MIMO, which is the key technologies in, you can say, in 5G and advanced 5G deployment, where the base station can have large number of antennas. So if you see the complexity with respect to number of antennas at the base station, we can again see that the proposed receiver is having much, or you can say drastically lower complexity in comparison to the conventional receiver being used for high mobility applications. Yeah, so to get the more detail in this domain, these are the papers. You can refer the papers. Yeah, this is the last slide for me. Thank you.
Thank you, sir. Next, we have Dr. Amrita Mishra. She's a faculty member at IIIT Bangalore here. Her research interests include applications of signal processing and machine learning for 5G and beyond, millimeter wave communication, and sparse signal processing. I welcome Dr. Amrita for the talk here.
Thank you, Priyadarshini, for the introduction. Good morning, everyone. I'm Amrita, and today I'm going to talk about the title. So today we are going to talk about channel estimation, sparse channel estimation in intelligent reflective surfaces, or IRS-based millimeter wave systems. IRS is otherwise a popular term which is used in literature is RIS, or reconfigurable intelligent surface. So to first understand what exactly is an IRS, it is nothing but a planar arrangement of low cost and small elements which have the capability to induce an adjustable phase shift on the incident signal. Now, why it has been touted as one of the most popular technologies to be associated with future communication is it is going to be cost effective because it comprises of small metamaterial based elements. It is adaptive in the sense we can change the amplitude and the phase of the incident signal, and the way the structure is going to be, it will be thin composite material sheets which can cover walls, buildings, etc. So it is practically realizable. The other interesting fact is, as Professor Das rightly mentioned, energy efficiency is one of the key things which we are looking for in modern communication systems, and IRS will help us in realizing that particular dream to some extent. Why? Because it does not require any kind of dedicated energy source per se for processing, decoding, encoding, or retransmission, unlike relay-based communication, where these relays are active devices and require separate energy sources. So they are nearly passive in nature. Further, they do not do any kind of noise amplification, which is another problem related with having active devices. They do not have any analog to digital converters or digital to analog converters, any kind of amplifiers, filters, etc. Having said all of that, they help in modifying the impinging signal to be able to meet the desired criteria. So which desired criteria are we speaking about here? That is what the whys of IRS is. So IRS can be used for extending the range of communication or to achieve a coverage extension for both indoor and outdoor scenarios. Having said that, this can be achieved without any additional energy requirement because the elements, the IRS elements, are passive in nature. One can also achieve physical layer security, which means if we have an eavesdropper, with the help of an IRS, we can cancel out the signal which the eavesdropper is trying to listen, thereby making that particular communication null and void. We can also support massive connectivity in terms of having a large number of users in perverse scenarios like cell edge and dead zones, where the typical signal strength is very less and normal cellular communication would fail in such kind of scenarios, and many more to this list. This is just a diagrammatic representation of few use cases where IRS could be deployed. Now, to answer the question, how do we then do it? To understand that, the traditional assumption in conventional wireless communication is if we have the intervening wireless channel between the transmitter and the receiver, which introduces some kind of distortion, the way we deal with this distortion is either at the receiver by designing some nice signal processing algorithms, or by pre-distorting the signal at the transmitter end, which requires again extra signal processing to be performed at the transmitter side. Now, IRS helps us break away from this conventional notion of wireless communication by saying that now we can work around this wireless channel and make it programmable, in the sense we can now induce some kind of a phase shift and an amplitude shift such that the effect of the wireless channel can be countered on the go or on the fly when the signal is on the way from the transmitter to the receiver. Now, to talk about the standardization activities, the initial testing was performed by one of Japan's very popular telecom service providers, NTT Docomo, and it started as early as 2018. And various institutes and organizations and industries all across the world have been working significantly on prototype building and proof of concept testing. However, the standardization work currently is at a regional level of SDOs. Two organizations in China, per se CCSA and Future Mobile Communication Forum, they have submitted a proposal as a study item, and the technical report is awaited to be published. Similar efforts has been done by the SDO in Europe, ETSI. They have formulated a industry specification group to look at the technical reports, proof of concepts, etc. in this particular area. In the release 18 of 3GPP in September 2022, as in the technical report, a work item was approved for something known as a network controlled repeater, or NCR, which is very close to IRS. And the standardization work has already begun. So both of them offer coverage extension, but there is difference in the sense NCR is based out of a mature technology, which is a sophisticated wireless repeater, and IRS looks at metamaterials and is a completely new technology. The ITU report, which was published on future technology trends for IMT systems of 2030 and beyond, recommends that IRS needs to be incorporated as a critical component for 6G networks. So we can hope that IRS be included as future study item and work item to be a part of 6G standards in future releases of 3GPP. Now, one of the aspects which me and my group at IIT Bangalore has looked at is IRS-based channel estimation. If we could look at the diagram on the right, there is a direct channel between the base station and the user, and we have a plethora of conventional algorithms to estimate it. Now, what we are looking at is how do we now estimate the channel from the base station to the IRS setup and the IRS setup to the user. That is done using the concept of cascaded channel estimation, where we say that we do not have the capacity to estimate each of these individually. Why? Because as we mentioned earlier, IRS is a passive setup and does not have any signal processing capability. That is why we want to estimate this cascaded channel, that is the combined channel from the base station to the IRS setup and the IRS setup to the user. And with the help of that, we should be able to do the other aspects which IRS wants to do, that is adjusting the phase shift here. Now, the key challenges with respect to IRS-based channel estimation, as I just mentioned, it is passive in nature, so it cannot do any kind of signal processing, cannot transmit pilots, and hence this needs to be accounted for. And this is where we actually take a departure from the conventional wireless channel estimation schemes. Now, typically, we want to have high gains, which means that the number of IRS elements here should be high, which implies we have a large number of extra coefficients to be estimated, which is of the order related to the number of base station antennas. In a massive MIMO setup, this can go to the order of hundreds and thousands, depends on the number of IRS elements and the users we are trying to serve. Now, conventional IRS channel estimation, it estimates cascaded channels, can be deployed for both time division duplex TDD or FDD. However, they suffer from a very major shortcoming, which is it requires a large number of pilot or known signals to estimate all the cascaded channels when there is an increase in the number of reflective elements on the IRS planar array. So the question So the question we ask here is, can we do something better? And the answer is affirmative. And how do we do it? So sorry for the, as Dr. Summer said, it is Murphy's law. Quite applies to me most of the times. So the way we do it is by leveraging spatial sparsity in millimeter wave channels. So what do we mean by spatial sparsity? If we could look at the picture on the right, we know that the base station and the IRS setup are going to be at elevated places wherein there is going to be only few paths spatially linking the base station to the user equipment. So here, if we could see, out of all these spatial angles, of course, this is just a 2D realization where we have only considered the angle of azimuth angle and not the angle of elevation, but it can be extended to the 3D case. We can only see here that only few spatial angles are active because there is a small number of scatterers which surrounds the base station as well as the IRS setup. Because of this, what happens is we are going to have this kind of a realization of the virtual angular domain or VAD based channel matrix, where out of so many possible realizations of angle of departure here from the base station and angle of arrival at the user equipment, only few of them are active, which renders the overall channel matrix in the virtual angular domain to be sparse in nature. And that is what we leverage in our work. So we express the cascaded channel matrix for the IRS setup using this representation, where we are sandwiching XK via two matrices, the dictionary matrices U and V on the left and right. They contain the array steering vectors corresponding to these AODs and AOAs. X is a sparse angular cascaded matrix, which will look something like this. So here we can see out of so many elements, only the elements which have been marked in blue are non-zero. Now, if we could use some mathematics and show how the input output receive system looks like when I sandwich xk, that is this matrix, with the dictionary matrix, a known dictionary matrix on the right, it is going to have a row sparse structure, which means out of so many rows, only particular rows are going to be completely non-zero, whereas the remaining rows are all zeros. And further, the elements of this row are correlated. So can we exploit this row sparsity as well as correlation amongst the elements of particular non-zero rows to do channel estimation? And again, the answer is in affirmative. We do it using a Bayesian learning based method, a temporal correlated multiple sparse Bayesian learning approach. Now, this is a generic algorithm which is available in literature, and we have custom made it for this particular case of cascaded channel estimation in IRS systems. So the idea is very simple. We associate a hyperparameter, an unknown hyperparameter, and an unknown covariance matrix to each row of my row sparse matrix X bar, and then we use an expectation maximization approach to estimate these two unknowns. Now, the fact that we used temporally correlated multiple SBL, it allows us to look at maximally sparse solution. So the convergence with respect to maximally sparse solution is achieved. Plus, this gives us the flexibility in the sense, since there is no fixed prior assignment, unlike the conventional sparse signal processing algorithms, we needn't do any heuristic fine tuning of user defined parameters to, look at the accuracy versus the level of sparsity. So that kind of adjustment needn't be done. So to look at the flow of the algorithm in a nutshell, so we take the received matrix as the input Y, and then the dictionary matrix. The coefficient matrix corresponding to the IRS is assumed to be known to us. That is also taken as the input, and the maximum number of iterations which we could do. We, of course, start the algorithm because this is an iterative algorithm. We need to consider some initial values. So we do some kind of an initialization, a very layman initialization of the unknown vectors. Then we evaluate. So I have not put the expressions for these quantities here, but the idea here is I'm going to evaluate the a posteriori mean and the a posteriori covariance associated with the row sparse matrix, the unknown row sparse matrix X bar. And then we check for convergence and stop only if convergence is achieved. Now I would be concluding very soon. So to understand the simulation results, let us first look at the simulation parameters. So here we have considered the number of pilot frames B to be 30 and a moderate SNR value of 15 dB and number of base station antennas to be 64. Now the existing scheme, which is the curve marked in blue, when it is considering as many number of IRS elements, L, as that of the number of pilot frames, it performs well. But as the number of IRS elements increases, which means we are having lesser number of pilot frames, we are having more spectral efficiency, but we are looking at condition where a practical condition where there will be a large number of IRS elements, the existing scheme starts performing very poorly, whereas the proposed Bayesian learning based schemes have a rather gradual increase in error in comparison to the existing scheme. So with this, I would like to thank my IRS group at IIIT Bangalore, Professor Priyanka, and my MSR student whose work is this, Agrim. So this brings me to the end of my presentation. Thank you very much.
Thank you, Dr. Amrita. Next, we have Dr. Priyanka Das. She's an assistant professor with IIIT Bangalore here. Before joining IIIT, she worked in Nokia Solution Networks and Dell Research and Development. Her research interests include cognitive radio, MIMO, physical layer security, and intelligent reflecting surfaces. I welcome Dr. Priyanka to this forum.
Thank you, Priyadarshini. Let me start today's presentations. I am going to speak about the security aspect, and we will be focusing on the physical layer security. And the technique that I am going to propose here is the optimal relay and antenna selection. So this is the brief outline. First, I will state what is the typical security approach that we are relying today in our mobile phone. That is the cryptographic based security. Then we will see why we are talking about the other dimension of security, that is in the physical layer domain security. Then I will state key physical layer security technologies, then our research, and then summary. So to see the mobile network security landscape, where we started with 1G and where we are in the 5G. So you see that as the time progresses, we start with 1G with the voice, and what are the typical frauds or the malwares? If there is a eavesdropping, and no, we do not have the digital domain, we have the analog domain. So we don't even think about the encryption and decryption algorithms. When we go for the 2G, that is the voice, and also there is a flexibility of the messaging, texting, you have some spams and also the false base stations kind of an attack. Moving further, when we talk about the 3G in 2001, when our internet is going to start along with the voice message, voice and also SMS, then the type of security challenges faced is typically different. We talk about virus, spywares, malicious apps and all. Then coming to the 4G, when we also talk about the internet, we are widely using internet in that. Then some other threats are also added on. I'm not going into each of the in detail, but there are some list. You can see the advanced persistent threats, distributed denial of service threat, and also the existing eavesdropping attack and so on. Now coming to the 5G where we are now, we also talk about the cyber warfare. So what does it mean? It's basically you want to attack your enemy country, what China and all are doing now. Maybe you use the attack in the cyber domain. Also, people have talking about the critical infrastructure threats, which is nothing but we are all connected world. The IoT is bringing into place. So we can think about the critical infrastructure threats, meaning you can attack in different varieties of the infrastructure, agriculture, education, finance sector all together now in one shot. So exploring the next what to do, right? So let's say we are in 5G and we want to see what is the future aspect of 6G. The 5G main three pillars, EMBB, URLLC, MMTC, they are going to be extended to certain extent so that you can exploit the different advantages in terms of reliability or latency or massive machine type communications, performance improvement, bigger data rate, much throughput and all. So we are talking about different dimensions. Now, when we come to the point of security, let me know which applications you are talking about. Then I can go into that depth in the security aspects in more detail. So coming to the applications, how many applications do you see? We have enormous amount of list in 5G and extended to the 6G. We have e-health, autonomous driving cars, smart grids, wearables, smart homes, industry 4.0, drones, also with your AR and MR applications. Now, my talk today is focusing on the basically the smart grid, or we talk about the IoT based security approaches. Coming to the standardization efforts, so there are basically different entities that are putting their hand together: 3GPP, ETSI, IETF, ITU8, and IEEE. So looking into the different horizons of their thoughts process, securing the different applications, there are enormous amount of list. For example, it starts, let's say, with release 15, massive machine type communications, proximity based services. They are all looking into different aspects of securing different type of applications: authentication and key management, security architecture, and also the release 18, they're talking about securing the personal internet of thing network, real-time communications, satellite access, and also today's AI ML based applications. So now the use cases they are talking about, there are different use cases. You can see that IoT smart city, V2X services. Let me focus into one of the aspects here. We focus into the smart city and IoT. We all know everything what is the Internet of Things today's world is all about. Now looking into what is the concern that we are talking about security, because we all are doing in wireless channel. Now wireless media is a broadcast media, so there will be a legitimate receiver who is actually the signal is going to his or her domain, but there will be a third party which is called the eavesdropper, who wants to overhear your message and wants to do some kind of disrupting the communication. So IoT data may contain several personal information, finance sector information, and so on. So now let's see what kind of techniques that we are relying on today's domain to secure the data, that is cryptography. We are all talking about the cryptography way of securing the data. The major feature is encryption and decryption. Encryption, you have the plain text, you convert to the unreadable ciphertext. And decryptions, from the unreadable ciphertext, you go back to the plain text. How do you do that? We have very famous algorithms coming into the place, which is symmetric key algorithm, or public key cryptography, or the hash function based algorithm. So more or less what you can think of, that they are all key based encryptions algorithm, trying to make sure your data is going to send from one node to the another node quite securely. Okay, now depending on what type of applications you are talking about, you will choose either symmetric key versus public key or the hash function based. Okay, now coming to the limitations where we pitch in. What are the type of dimensions you can think about that cryptography is not at all sufficient for future generation? The first thing, cryptography has to be operated, it needs a computationally intensive operations, which is not at all energy efficient. Second thing, you are talking about ultra reliable low latency communications. How long will you wait? 25 millisecond, 1 millisecond, 125 microsecond. Again, the cryptographic based security might be not enough to meet this latency constraint. The third and most important point down the line, 20 years, quantum cryptography. So when we talk about the eavesdropper has unbounded computational capable devices. What does it mean? It will break the encryption and decryption algorithm. It will generate your password so that it can hack your system quite easily, so that conventional cryptographic techniques will not be at all workable in that big picture when we come into the quantum crypto. So you need to think about there are other mechanisms by which you can actually make your system quite secure depending on the diverse applications of 6G. So here comes the another way techniques, and the research is focused on securing your data in the physical layer itself, which comes to the generations of the term physical layer security. So what does it physical layer security actually try to do? Let's focus on the two aspects. One is crypto, another is file layer security. Coming to the left hand side, cryptography part. What is happening here? The bottommost layer is the physical layer where your signals are coming in at the receiver end. It will go for demodulations and decoding to generate the bits. Now, the topmost layer is the applications layer where the conventional cryptographic techniques, algorithms are all running there with the help of the secret keys, and you are getting your secure message at the top of the stack. Now, on the other hand, when you go for physical layer security, entire the dashed line, which I can show in this red line, that is shifted entirely to the physical layer. What does it mean? So you want to secure your techniques by doing some sophisticated physical layer development or technologies entirely in the physical layer. So coming into this, so what you get is basically the secure bits out of the physical layer, so that you do not have to rely on the key based techniques which is running on the application layer. But there is a punchline, whether only physical layer security will be sufficient, or if I want to protect on a very broad way, both of them has to be together. And there is a talk about cross layer security. Okay, so coming to the physical layer security, it has main two advantages is crypto security is compromised if the attacker is very powerful. Physical layer security cannot be compromised because we do not rely on the computational power in the physical layer security. The second thing, there is no key distribution and key management problem which is arising in physical layer, which is the most important problem for the cryptographic security. Okay, now coming into the depth, how does PLS work? So physical layer meaning you have the broadcast channel. So you exploit the randomness of the wireless channel to secure your message from Alice, which is my transmitter, to Bob, which is my legitimate receiver. There is a third party which is called eavesdropper. He wants to overhear this actual information, wants to attack that. Okay, now coming to this, how does this will happen? So this is the overall idea. I'm just going to float here. What are the typical file layer techniques that will stand and say, I'm there to save your data in the physical layer? Number one, MIMO. We are all talking about MIMO. The MIMO beamforming is a very, very good technology. It can beamform to the desired directions, and it can save a null to the directions of the eavesdrop. Second is antenna selections. You do not want multiple antennas to be used. Well, you use the best antenna, which will give you energy efficiency in terms of reduced number of radio frequency chains used. Only one antenna, you need one RF chain, not multiple RF chains. So you save energy, and also at the time, by properly choosing the best antenna, you can make sure your data or the secrecy rate is maximized towards the legitimate receiver. Second is artificial noise. The third is artificial noise. What does it mean? Instead of sending the actual data to the Bob from the Alice, you also send a noise signal such that the actual signal is shown now to the Bob, but it will show the range space for the Eve. So I'm going to send some signal, which is a noise signal, such that my eavesdropper will be confused whether the Bob will get the data perfectly. How does it make it? Again, linear algebra will pitch in here, so that you design your AN space which forms in the null space. of the signal from Alice to Bob, so that you will get a destructive signal at the legitimate receiver, but a constructive signal at the eavesdropper. The third is the where we come for the cooperative relaying technique. This is also another useful technique. Now, I will come to this, and also we are talking about cooperative jamming and the more intelligent reflecting surface, which will also helpful for file-layer security. As Amrita pointed out, it will do a passive beamforming so that it will give more directions, more directional beam to the actual receiver and then null to the eavesdropper. So our team here is looking into the PHY security by merging two techniques, which is the cooperative relays, which is shown here, and the relays, the antenna selections, which is shown in the right hand side of this. So what does it do? You have a lot of cooperative relays that are nothing but they are helping node to forward the data, and also you have a lot of antennas. If we consider the multiple antenna assisted node, then you do the antenna selections. So by combining the best relay selections and best antenna selection jointly in such optimal sense, such that you make sure your secrecy rate is maximized, or you can benefit by using the techniques which is lying on the physical layer as such. So there are some problem statements. I'm not going into depth of the actual problem statement that we are looking in our lab. So by summary, security has a big impact wherever we talk about 5G and beyond 5G, 6G. Everywhere we are talking about securing the data. Scalable, adaptive, and quantum security is very, very important so that we can do our day-to-day communications reliably and efficiently. PHY-layer will pitch in next few years, and the research is already happening for last 10 years. The research is going on. Which is not happening is the test bed development for physical layer security as such, or whether we are talking about the standardizations of physical layer security, because we have seen the standards body already developing security from cryptography point of view, but the standardization aspect for 5-layer security is yet well open nature. We have to put it in the standards so that actual implementation can happen for the robust future generation. Thank you.
Thank you, Dr. Priyanka. Come down. So for next topic, we have network slicing. The initial part would be covered by Dr. Das, and the next part would be covered by Professor Jyotsna.
Okay, 10 minutes. Okay. Mine 10. Mine 15. Jyotsna is 5. It's on? It's on? Okay. So thank you. And so you see, thanks to the Professor Amrita, Professor Priyanka, and Professor Prem have talked about various layers of the security and the 5-layer, and Prem will be talking about the hardware and all. And each of these problems are very complex and critical. But if you ask me, you must have heard everywhere, if the 5G and 6G has to be successful, everybody talks about network slicing. And network slicing, everywhere we say. But the conceptual and fundamentally understanding the problem is very, very important, which I will explain to you. But if you ask me, I will tell that network slicing is the mother of all these daughters. On a physical layer problem, security problem, these are one daughter. If I take it, if you add all of them, this is the mother of the problem, because it is the end-to-end efficiency, network slicing. So end-to-end efficiency means if you slides changer. Okay. If you want to, I'll show you quickly the slides and explain to you. So you please be on the board when I will put my finger, or I'll pointer towards that and show you. So, so if you understand the problem, then you will appreciate the research all, happening across the globe on this issue of network slicing. I thank my colleague Professor Joshna, who has been doing a lot of research along with our research students in this regard. But let me go one by one slides. Okay, so I'll be talking about the concept of the network slicing first, then the evaluation and implementation until today. The concept part is very, very important to understand the complexity of the problem, how deep it is and how difficult. If 5G and 6G will be successful, then network slicing has to be successful before that, because it will carry all the layers of the networks, and also end to end. Both are important. And work done IIIT in IIIT Bangalore by Professor Joshna will be talking about that, or network slice service and resource management, on-demand network slicing, adaptive network slicing, security implication, and published work. So let me go to the next slide. See, this is a very, very familiar picture of in our undergraduate life, starting that 7-layer structure, the PHY, data link layer, and these two layers have been standardized, because if you know 4G, 5G, 6G, this is 3GPP or 5GPP or IEEE. IEEE works on Wi-Fi, and WiMAX it worked mainly Wi-Fi, and 3GPP is working on your 5G now standard, 5-layer physical layer and the MAC layer. And all the higher layers, if you look at network layer, transport layer, sessions layer, presentation applications, this comes from IETF standards. That is called Internet Engineering Task Force, who makes the standards of the routing, transport layer, TCP protocol, UDP protocol, and also all those applications that are also coming. And there is a W3 World Wide Web also slowly coming in the applications layer for standardization. Okay, so coming to the point is that why the slicing problem is so complex. I will explain to you. Before that, let me quickly show you this. Why layering structure? Because you must be knowing, dealing with any complex systems, networking is a very complex system. It's a, because we as a user, we want to send a WhatsApp message and it has to reach the destination. We want that it has to be in a fraction of a second and has to come back to us. But have you ever thought that you are in a Wi-Fi, you may be on a 4G or a 5G, and backbone is optical, which we don't able to see, and there are hundreds of routers till the destination, if the destination is in the United States, and every router is a different kind, every switch is of a different kind, and you are using a protocol of different kind. User equipment, my mobile handset and your mobile handset are also different. So much of heterogeneity, but we want the results to go there and come back immediately in a fraction of a second, many millisecond. So solve that complex problem, we have a layered structures, and in the layer structure, these are the layers. Okay, so now till 20 years back, each layer was distinctly different. That means if somebody is doing a research in physical layer, he don't need to do on data link layer. Data link layer person doesn't need physical layer or network layer. Network layer used to work on network layer. He doesn't know about all of this. So deep research happened very much in narrow in each direction, and they did research and performance evaluation on that direction. But when the time came in recently, if you look at, then this if you look at this, in this transport layer, I'm just recollecting your memories, which you are very much know, only two protocols, TCP and UDP, practically there. And where is they? They're in your operating system. And TCP transport control protocol and user datagram protocol. And if any application, whether I'm doing a real-time, non-real-time communication, I have only two options: pick up TCP and UDP. And TCP has a very interesting many sub protocols inside TCP. One of them is called congestion control. Congestion control means I will send one packet, which I have written at here. You can see here. I will send one packet to the destination. If destination is, say, think United States, so much of delay goes. If successful, I will be allowed to transmit 2 packets. If 2 are successful, then I will allowed to have 4 packets. If it is a cubic, 3, 9, like that kind of. But this is completely standardized and it is in your operating system. You have no control on it because you have to pick up that. And this is one of the bottleneck, because in applications we are talking about the millisecond, 1 millisecond, 5 millisecond of delay in case of ultra reliable low latency. in case of 5G. But 5G is only from your mobile device to the base station. Backbone is optical. You don't have any control on that. That is a different kind of standards. So look at the complexity of the problem here. I have not done here applications there. Here also HTTP protocol there for browsing, or for voice protocols are there. So they are different protocols. Let me come to the network layer. Look at the so in the network layer, only I have similarly only two options I have. Only OSPF, open standard path first, and BGP, border gateway protocol. If I am in a small WAN or my own wide area networks or a small metropolitan networks, I have OSPF or border gateway protocol because interworking. So and also datagram or the multi-protocol level switching which came, but the first control packet again uses OSPF for BGP to reach from source to destination. So if we do not have a much options with respect to number of applications, what I wanted to say, we have a very much limited protocols available by default on the backbone. And now comes your bottom two layer, which is 3GPP, 5GPP, or the IEEE is talking of bottom two layers is optimized very much. When physical layer, data link layer, lot of research happening for last 10 years that will give you example that if physical layer wireless medium is not good, and then MAC protocol changes on the fly, that new different kind of MAC will be picked up. For an example, if the wireless medium is very bad, you are moving 120 kilometers per hour, or then your wireless communication to the base station is bad, then ARQ, automatic repeat request kind of MAC protocol also changes, because you have to send the same packet 4 to 5 times to be successful, and each time repetition is 7 millisecond of delay at least. So 7 into 5, 35 milliseconds is gone for transmission, only the repetition. So if you look at this is getting optimized, but what about this? So I'm quickly repeating it here because I brought that same slide from this slide to make you understand that these two layers is getting optimized, but higher layers are not optimized according to applications, because I have only two options in network layer, OSPF and BGP and MPLS, and TCP and UDP in the transport layer. If I go and higher layer, my options are less. But I am asking as a 5G user with URLLC, EMBB and all, give me less than a milliseconds of delays or few milliseconds of delays. But this is not possible with respect to this architecture, because we are always, whenever we talk, you'll see we are always concentrating on these 2 points, these two layers in 5G standardization and all, 6G standardization and all. So when we are saying that we are moving from 5G to 6G, we should include higher these 4 layers. Without that, we will be never be successful as network slicing is concerned. How to solve this problem? So now to solve this problem, we have to invent each of these layers. Upper layers not optimized with application. Upper layers are not. These top 5 layers, if you look at, bottom 2 you leave it, this not being optimized. That means the moment I ask a driverless car application, or if I want a robotic operations from a distance, my applications needs a 5 millisecond of delay, which is being not optimized with respect to TCP. TCP is the old one, 50 years old, and it has no those kind of concepts of high-speed communications, because I need a reliable communication, and my routing algorithms also not so much efficient to give you quickly destination a path. Okay, so I have to think of completely from top to bottom optimization. So then how network slicing is going to solve it? What is that concept then? Now I'm coming to the next part is very important. Look at it, then you will understand that where we are going. So if I want to do Aadhaar means I am going to airport, I need to authorize authentication of mine has to be done. So if I have given a 1 second, in India people are highly impatient. If you are standing in front of queue, piche 5 aadmi will be standing behind you, they'll say go quickly go, because they are long queues always in India. So if you have Aadhaar, I took that example of India, and you will be given a 1 second. 1 second means 1000 millisecond. Out of the 1000 millisecond, there are 3 parts, major 3 parts. One part is that the moment you put your thumb, then it has to go to the Aadhaar in Delhi, that is a database, and it has to come back telling that it is you. What are the 3 parts? First part is communication. The moment you feel the communication from here to Delhi again in the data center, it has to go in. There is another network, 2 networks. One is from here to Delhi inside the data center, and in the 1.4 billion database, he has to search delay. That is the second one. And third one is after the communication comes, then the electronics device displays the delay. It is a much more higher than our communication delay. So if 1000 millisecond by 3, if I take it average, so 330 millisecond is only on the communication, which I have to solve at here. So look at this. So 330 millisecond, I have to invent a applications layer protocol which will be doing the communication from here to my device to the destination and come back. And I have to, that is called applications layer protocol 1, which is not classical HTTP 1 or HTTP 2, all kind of things. TCP 1 and or UDP 1 I have to invent, and routing protocol 1, MAC 1, phi modulation 1, which only dedicated kind of other kind of delay. Other kind of applications, there are multiple will be there, this kind of delay, which will be not be true if I'm using a driverless car. So we are only concentrating on bottom two, but now what I am saying to say, this TCP which is only have a congestion control will not work at here, because congestion control is damn slow. So we have to invent a TCP2 which is a reliable, TCP stands for reliable communication, and that one packet sending, one packet receiving, that will not work. So this is another set of protocol I have to invent and keep it as a software stack inside your system, which can give you that end-to-end slice kind of things. So now last example, I'll show you video games. This children, summer vacation started. Now children will be playing video games, and one will be sitting at here, one in Delhi, one in Bombay, and everywhere. And this video games needs a lot of online 50 millisecond delay according to standards. So if I online killing, so I have to have a different set of protocols. So this is for 1 millisecond to 5 millisecond delay. This is for 300 millisecond and above. This is only 50 to 100 millisecond. So three of them, 3 sets of protocols, and optimized from top to bottom. And this 3 set is called, if you look at it very carefully, now look at it. This, in your own system, in your own router or your own UE, if I am doing video games, I'll be using this set of protocol. If I'm using for other, this set of protocol. And so this is like a one slice of protocols inside your system. When I activate this, my hardware requirement in the file layer will be different. My hardware requirement, this one is different, this one. So this one, so this is called, if you look at, this is one slice in your system, this is another slice in your system. So this is not only in the UV, this will be in the base station also. So the optimization of that is your problem, end to end. So it is the mother of all the problems what you see. Each layer has to be solved by optimization here. If you solve for that, only people are talking about network slicing in 5G and 6. If it has to be successful, then this is a much complex problem from top to bottom, and every layer has security which just pops up. So that also get added up into that. So if you ask me, then this slice what you see vertically, now I will make it horizontal. Just look at this, how it will look like. So then you can understand the problems everywhere. See, this is the infrastructure, okay? Same infrastructure. This is these blues are the routers, cloud access nodes. These squares are the access nodes, the cloud nodes. These are, and these are the part of the slide. So this infrastructure is same. That means same base station, and behind the base station, routers and switches are same, connected by optical networks. But in front of that, there is an. So if I am going for a smartphone EMBB, then I will have a one slice of resources required, which I showed you that verticals one like an horizontal here, and this is for automotive driverless car, another slice. So same set of routers and bandwidth will be giving you different protocol optimization requirement of resources. So for that only it is calling as a network slicing. But it's my point. So now in the previous slide, again I'll go back for a second. So this one, what you see, the top to bottom, according to the applications requirement, this slice, this is a slice of protocols which need different resources, spectrums, memories, bandwidth, and all will be provided by the infrastructure in a horizontal mode. I am showing it because end to end. So this is slice. So this is a way from the moment you start any application till the physical layer and across the network, or quickly it will get optimized. Then you will get the benefit of 5G and 6G. Without this, we cannot get. So this problem is, for that only I said with a just to give an example, is a complex problem. And so this is the thing, if you look at quickly, sorry, I've run out of time, but I will take quickly 2 seconds before I hand over to Josna. So this one, if you see 3GPP network slicing, so this one is a one slice, same infrastructure, hardwares, softwares, but inside that the protocols optimization will be happening. This is the one slice on EMBB, because for each one you will not put a different base station. One base station will be giving you EMBB communication, massive machine type communications, that is IoT, and URLLC communication. But how much resource will be allocated from that base station depends on that slice optimizations. Each slice will have a different optimizations. So this is the network slice selections, how you'll select. The moment you start any application, so the moment you come select any applications, so this kind of signaling will start from UV, G node B, how much spectrum you need, how much memory you need and all. Then it will go to AMF, those core networks behind the 5G and all. So this is only 5G part you see, or 6G part. But behind that, till the destination, the moment this is below the base station, this core network, or close to the base station, a cloud or edge network, behind that there is a thousands of kilometers of optical network till you reach United States or Europe. Again, when you come out from the optical network, there is again a 5G network or 6G network. Last and mile. First mile, last mile is 5G or 6G. In between optical, end to end slicing has to happen. So this is the concept of that. So I will, these are the things, you know, release 15 people have worked, and I will show you in current plan in release 18 people are thinking about that, which we have been talking in IIITV for last 4 years or more than that. So I will come to this one. As you see here, 5G new radio user equipment UV full stack. Look at this, full stack testing for network slicing. What is full stack then? Full stack means from top to bottom, but they have not used the word optimization, protocols and all. This is a huge another 5 years to or more than work. Hardcore research is that, because 2 layers we took 15 years, physical layer and MAC layer. Till now people are working. You'll think about all the 5 layers, TCP layer and TCP layer, network layer. It's extremely difficult. They are the foundation of the networking. So touching it means you are touching the foundation of the whole communication. So it's a very complex how to do it. So in this, I will hand over to Professor Jyotsna quickly to, if you, so quickly I will go through that. We are doing on this work in the IIITB is that for the end-to-end communication. So there are 3 things are there. One is called virtual packet gateways, and these are the packet gateways in the base stations, and also virtual service gateways, SVGs, and virtual mobility management entities. So because of the base station part from here, this is the RAN part, this is the core network part, and this is the backbone network part. So all these 3 things, how to optimize with respect to spectrum, transport and all. So these are the things we are working on here. And you can see the flexible RAN services, RAS, has to be optimized for that from here to here for this slicing. So these are the you want to speak? Sorry. So come. So Professor Jyotsna will be focusing on the research problem which we have solved right here, and we'll try to.
Thank you, Professor, for the very motivating and inspirational speech. Next, we have Dr. Jyotsna Bapat. She's a professor and dean faculty with IIIT Bangalore here. Before joining IIIT in 2006, she worked as an assistant professor with Fairleigh Dickinson University in USA and Lucent Technologies in USA. Her research interests include network slicing, scheduling in 5G, privacy and security in IoT systems, and broadly networking and physical layer aspects of wireless communication.
Thank you, Priya. I promise I'll be real quick. I have the pleasure of coming after Professor Das, after that great explanation, and before lunch. Not a very good slot. So I'll try to cover it as quickly as I can. Okay. As Professor Das mentioned it very, very clearly, this is a difficult problem. Okay. This is not quite listening to me. You are talking about the network slices. Operative word here is these are also the logical connections. So the network slices will need to be formed, and also when there is no requirement, they will need to be dismantled as well. There are several UAs which are going to come into the network depending upon the situation that is present. Each UE may have different requirements, and as was also mentioned, each UE may have different requirements in the sense that you might be making a video call, you also might be looking at your home security systems. So here, as everybody knows, in 5G, we are looking at 3 different types of services: URLLC, EMBB, and MMTC. Your requirements need not always exactly fall into that, but you may need access to multiple slices. Okay. So to just give you a brief idea, most of our research work in this, which has been done by our PhD student, Sharvari Ravindran, and also Yogita, who is sitting here, she is looking at the security aspect of it. So broadly, our focus has been on resource optimization. How do we allocate the resources such that the quality of service requirement, the service so-called the service level agreements are met, while at the same time, the occupancy of the slices. We would like to reduce the number of slices that are underutilized or overutilized. And while all this that is done, at the same time, when you are looking at the different physical layer conditions, the way the UE is connecting, as well as at the transport packet network as well. So just looking at this, in this paper, we were looking at a single UE which is hosting multiple applications. So most of these applications that are there, they also have, these are the, some of them, they're a resource dependency, and based on the resource allocation is done. I'm sorry, this seems to have a life of mind of its own. It just changes the slides whenever it wants to. And so, okay, that doesn't matter. I'll be done rather quickly. So we are looking at a pretty formidable looking cost function here. So you are looking at maximizing the throughput, efficiency, and the scalability. And all these things need to be done while looking at the certain constraints that are there. Obviously, some of the constraints are looking at the kind of quality of service requirements that are needed. Okay. One more part. So there are, I won't go over each one of these slides. I'll just give you a brief overview now. I also have the list of publications. Anybody would like to look at it, feel free to reach out to us. One of them being the slice inside the slice, wherein we are saying every tenant who is occupying a slice should be able to run other services. For example, within MMTC, I might have different requirements. I should be able to run it recursively. I should be able to have my own sub slices inside this. This work was published in ANTS. And the second part which we talked about was the end-to-end network slice service and resource management, wherein, okay, can I just do up and down here? Yeah, just stay here, yeah, don't move, okay? So we have the request for the whatever are the requirements. Based on that, the service management and architecture model will be trained. This feedback, along with the policy-based guidelines, will be given to the distributed unit, and that will be given to the radio unit. Based on the feedback from the radio unit and the distributed unit, any changes that need to be made in the model will be made, and this will be repeated. I am going to, these are the little more explanations of this. I'm going to just show you the last 2 parts of it, which are the current work. Yeah. So here we are saying that yes, stay there. Okay, thank you. So here what we are saying is that every time a new user comes into the system, before you are allocating systems to it, there are 2 things that we are looking at. We are looking at what the user is requesting. At the same time, we are looking at some of the past behavior. We predict what the performance, what the requirements are going to be like. We use that along with the existing requirements, the existing channel performance, and use that for resource allocation. And we have shown that by using this, we are able to achieve efficiency in the system. The efficiency is typically measured in terms of the slice occupancy as well as how closely we meet the quality of service parameters. Next. And this is my last slide, the next one, I promise. No. Vishnu is in a hurry to make sure that is indeed the last slide. So this is the work we did have everybody talking about the security. So here we are talking about security in a slightly different way. We said that, look, there is a slice for MMTC services, URLLC, EMPP. Different users who are requesting the MMTC service will occupy the slice which is meant for MMTC. Now look at this. I have a smart home system in which I might be using, for example, to turn on my coffee machine, or also allow some guests to come in. I also have the different healthcare kind of systems, a machine floor. These are all present, all will be occupying the MMTC slice. What we were saying is that if somebody gains access to this slice by requesting it, because I have some MMTC service required, by using that, it is possible to introduce an attack to another MMTC system. There are two ways in which it can be done, which is shown by us. One of them is by using this information, I can start sending messages. For example, something like the IoT healthcare system, those messages will look like valid messages to all the devices that are present. They will keep sending the messages back. For example, I might be sending my readings back. It could be my blood pressure reading or anything, which is every half an hour or every 2-3 hours or something in my smart home. Instead of that, it looks like the system is asking me to send the messages far more frequently. So it is not an attack per se, but what will happen is that if I'm going to send my readings back every few minutes, my battery is going to drain very quickly. And if we are looking at a place where changing the battery is not easy, your system is going to get affected for a while. It's a very simple, at the same time, devious kind of an attack, and it can be done anytime whenever you're at the cloud and in the slice you have another user. So there are two systems. Your system might be well protected at your end, but if another system gets in, they can attack you via that. So the last two work, they have been recently been completed and they will be presented in Connect. Yogita, who's sitting in the audience today, she is the one working on this particular security aspects of it. Now, this is truly my last slide. These are some of the research work which has been done and published mainly by Sharvari, and it started under the guidance of Professor Das. Thank you very much.
Thank you, Professor Jyotsna. Next, we have a poll coming up. So I request all the offline and the online participants to log in to menti.com. We'll be showing the link here along with a code for you to enter. So a couple of questions on your familiarity with 3GPP standardization process. So please log into menti.com, that is menti.com. And please enter the code 36115277. So this is for all the online and offline participants. You can log into menti.com from your cell phones or laptops. We should be having pretty good network here, I guess. menti.com with the code 36115277. So we are having live results being shown. We have 3 questions in total, and once we have good number of responses for the first question, we'll be moving on to the second question. So we have more than 100 participants joining this workshop online. I kindly request all the offline and the online participants to vote for this question. In a few seconds, we'll be moving on to the next question. Is that good? Shall we move on to the next question? Next question, please. Only one vote per person. Huh? The next question is about if your organization is interested in making contributions to 3GPP in any of the topics that have been discussed today. So we've had many good topics, intelligent reflecting surfaces, network slicing, and a lot of good topics being discussed today. Please let us know if you or your organization would be interested in contributing to or working on these topics. If only our election results were also available this quickly. So we have about 75 participants online and offline voting on these. So let's move on to the next question if everyone's done. Even if you're not done with the second question, if you're logging in, all the three questions should be accessible to you. The last question. Is your organization interested in collaborating with academia or any other relevant organizations in the topics discussed today? Please let us know. So we have a lot of participants from several industries as well attending this workshop online. We would love to hear your feedback. Thank you everyone for your time and voting for these questions. This will help us in analyzing the status of progress that we can make on these topics, and we will be getting back to you, all the online participants who have registered, or also the offline participants. We have collected email ID and several details. There are also a lot of participants who have been asking questions online. So due to lack of time, we would not be answering them currently. We would be getting back to you. The relevant professors and industrialists would be getting back to you soon. And next, before we conclude, I would like to invite Ms. Pamela here. She is the ex-DGI of TSDSI, and she's been the president and founder chair of the Cloud Computing Innovation Council of India. I request her to therapy.
That this has been great being here and seeing the enthusiasm amongst the speakers to contribute to 3GPP. Looks like a lot of groundwork has been done. So don't be disheartened by Samar saying that the boat has left or the train has left the station. That's not true, you know. No, but you know, there is a way to get in also. So, but this is one thing we learned in ITU when we were doing 5GI. We were told from the first day that this work started 5 years back. You have come in 2017. You're too late. You should have come then. Go to the next G, right? And you know, the chair said no. You keep making your contribution till the last day when any new contribution coming has to be considered by the chair. It cannot just be rejected outright. Okay, so you may be making a placeholder for the next one, but go ahead, contribute. That's the only way to learn. Be there, contribute, even if it's the most stupidest contribution. There are a lot of people, you know, the 50 who come from our neighbors, they do make a lot of stupid contributions. So first thing is to just go there, contribute. Just contribute for the heck of contribution. That's what I would say. Thank you.
Thank you. Next, we have Mr. Guna B. Shekhar, he is a telecom storage and network professional with VLSI design background. He has spent 18 plus years at LSI Logic, which is now Broadcom, and about 5 plus years at various Silicon Valley ASIC startups at senior management roles. Thank you, sir.
Hi, I'm just going to take a few minutes to just thank everyone. It's been a great workshop. Appreciate Dr. Das for taking the time and hosting this. Your team did a wonderful job. Professor Prem, thanks for organizing the whole thing. And I mean, we could, each of these topics, we could probably talk for hours. And I know that you had a time constraint and you had to bring it within 15, 20 minutes. Thank you. Wonderful topics, very eye-opening, particularly network slicing. I mean, true merger of computing and communications. I think it's going to be an ocean, I guess, right? Getting deeper into that. So very exciting to see all the things, even on physical layer security, RIS and everything. So I'm not going to get into too much details here, but just want to make sure that Pamela thanks, everybody thanks Samar. Thank you for the introduction to 3GPP. Most importantly, the one important thing, the reason why we had started doing these micro workshops is to increase the number of contributions that are coming out of India, right? So that is like the primary goal. So when we started really looking into it, we looked at the total number of contributions that's coming out of India. It's still a very small percentage compared to the total number of contributions that's going into 3GPP, right? So we need to take this percentage to a different level, and we believe that India has a potential. And the reason why we are doing this workshop is to make sure that everybody is aware about all the contributions that are happening within 3GPP right now and how you can contribute. So we want, as Pamela said, we want more and more people to step forward and into the process, get into the standardization effort. And this is really going to make or break what we're going to do in the next 10 years going forward. So thank you, and thanks for the audience for taking the time. I know that all of your time is precious. And online audience, thank you for being there and answering the poll. And most importantly, can you just go to the last slide? I want to, there is a contact email, okay, microworkshop@tsdsi.in. So send your feedback, send your questions. If you want to contribute, if you're interested in some topic, if you want to reach out to the industry, whatever you have, right? Just send an email and we'll get back to you. This is one way to connect with whatever that happened today, any feedback, any improvements, whatever you want. Okay, so thank you, appreciate it.
There was supposed to be one more slide depicting photograph of the lunch being arranged, but I guess we can go in person and take. So there's lunch at third floor. I thank all the, unfortunately not for the online participants, only for the offline participants. I thank all the participants today for attending this micro workshop in advancing 5G towards 6G. So anything else to add? Thank you for this wonderful opportunity. Yeah, thank you all.